I now call to order the Society's 2,381st meeting in the 146th year since its founding in 1871. Good evening, everyone. Good evening. My name is Larry Milstein, as some of you know. I am the president of PSW, the oldest scientific society of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. We will begin with a few announcements, followed by a reading of the minutes of the 2,380th meeting, and we will then turn to this evening's lecture, followed by a question and answer period. Thereafter, I will present a small thank you gift to our speaker, make a few closing announcements, and adjourn the meeting to the social hour. Please join me in thanking the sponsors of the Fall 2017 and Spring 2018 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a generous sponsor who has asked to remain anonymous. We have the good fortune tonight, can I embarrass you, Paul, to have with us the president of PSO, who has been a generous and tireless supporter of PSW. Paul Rich is in the back, and I'd really like it if we could give him a warm round of applause. Thank you very much. In addition to his various means of support, he has also generously republished bulletins of the early society, and I think we're up to volume 12 or 13, and more on that at another time. I'd also like to let you know that longtime member Bill Maish, who passed away last year, has left us a bequest, it's quite generous, that we received earlier this week. Bill served the Society in many roles since he first joined in the 1950s, including serving as president. We recall him fondly. We recall his spirit. We hope that we can continue the Society as an organization in which everyone interested in science will enjoy membership throughout their lives, as Bill did. So I guess we can give him a round of applause also. He was a good friend. I'm also sad to tell you that former PSW member and University of Maryland professor Michael Ahern passed away recently. Michael gave a very interesting talk on deep impact not long ago after its mission to crash into an asteroid that's been successfully executed. We owe a good portion of what we know about comets to Michael's efforts over the years, and he will be sorely missed in the planetary science community, as well as by members of PSW. On happier notes, I'm pleased, as I mentioned at the last minute, to announce that Anne McQueen has joined the PSW General Committee in the position of Social Media Director. And we thank her for volunteering to do this for PSW. Among other labors of love that she will undertake, Anne will be tweeting for PSW. Please follow her on @PSW Science. And here are some examples. And she's already telling us about something interesting that relates to tonight's weather in space. Also, we are live streaming tonight's lecture. So if you're interested in looking at the live stream, go to YouTube, to PSW Science, and at the top you'll find the live stream, I suppose you call it screen, and all you have to do is press on the arrow and pick up the stream. Streaming is one part of our efforts to bring the best in scientific presentations and discussions to people now everywhere around the world, and eventually in space. And maybe the moon and Mars, when they get civilized there. So we do know that there's at least one person in Australia who is going to be watching, and we hope to hear from him and have his feedback. I am pleased to announce that the following new members have been elected. Ekaterina Maliu a public health expert with the U.S. Department of Health and Human Services with a specific interest in genetics, who comes to PSW through PSW member Frank Robert, the aforementioned Aussie who was going to be watching the live stream. And tonight's speaker, Antti Pulkkinen, whose interest will be obvious from tonight's proceedings. Please join me in welcoming them to the Society. No, I'm not trying to duck out of sight. For our new members, I have a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, which we are happy to have through Westphalia Press and the efforts of PSO and Paul Rich. I neglected to bring copies to the last meeting, so if you were announced as a new member then, please feel free to come up and get your copy of the Bulletin. And also tonight, if you have been mentioned as a new member, please see me to pick up your copy. The first volume is particularly interested, even if you're not that interested in the proceedings of science back in the 1800s, because if you're interested in PSW, you'll find out there why PSW was founded and why it was called the Philosophical Society of Washington. And you may infer from that why we prefer these days to refer to it as PSW and PSW Science. Recording Secretary James Hewin will now read the minutes of the previous meeting's lecture on Europa and other ocean worlds by Jim Garvin.
Good evening. It's October 6th, 2017. President Larry Milstein called the 2,380th meeting of the Society to order at 8:05 p.m. Being the first meeting of the year, this was the annual meeting of the Society. President Milstein summarized the annual reports of the officers and the Society's good health. He then welcomed new members. The minutes of the previous meeting were read and approved. President Milstein then introduced the speaker for the evening, James B. Garvin, Chief Scientist, NASA Goddard Space Flight Center. His lecture was titled, Searching for Signs of Habitability and Life on Other Ocean Worlds. Dr. Garvin began by noting the 30th anniversary of NASA's Voyager mission to the edge of our solar system. He then moved to discussing a nearby ocean world bigger than our own, Europa. The Jovian moon, first examined by the Voyager spacecraft, has a land area approximately the size of Africa, he said. Scientists believe this moon has an ocean that is volumetrically the size of our own here on Earth. Also like Earth, we have reason to believe this cue-ball planet is a dynamic world with a crust that deforms 100 feet per orbit due to its ocean. But unlike Earth, Europa lies in the radiation belts of Jupiter, which is not conducive to long-chain organic molecules that all humans are made of. Garvin said the best working hypothesis for life on Europa is a large 100-kilometer deep ocean covered by a crust of silicate ice several miles deep, shielding ocean life from radiation. This hypothesis is supported by reconnaissance from the Voyager and Galileo spacecraft. To be sure whether there is life on Europa, according to Garvin, we must go there. Garvin likened the vision for going to Europa to NASA's exploration of Mars. NASA sent the Viking spacecraft to Mars in 1976 to read the chemistry of the environment. NASA subsequently sent a gas chromatograph mass spectrometer landing on Mars in 2012. In the years since landing on Mars, NASA has discovered organics, a methane cycle, and chlorobenzenes, but not the life signs scientists were hoping for. For Mars, he said, the fun stuff is all in the past. Ocean worlds, however, present better prospects for finding life that is still present. Europa is home to the most accessible foreign ocean in the solar system, with liquid close to the surface and potential fissures in its ice crust. The exciting stuff, Garvin said, would be seeping or bursting through Europa's crust. But it has a short resonance time because of Europa's intense surface radiation. Today, NASA can land on Mars within 10 kilometers of its target, which Garvin calls exceptional. But the good stuff on Europa may be located within an area of only a kilometer. If NASA is going to land a static lab on Europa to conduct in situ analysis, NASA needs to improve its landing accuracy. So Garvin proposes to leverage the James Webb Space Telescope's spectral power to examine the chemistries of small surface areas to identify potentially fruitful surface areas. Then, the CLIPPER mission will follow in the early 2020s for habitability reconnaissance. CLIPPER will provide the requisite resolution to understand Europa's terrain and paint a picture of the surface in sufficient detail to accurately land a laboratory. After figuring out where to land, Garvin thinks a landing mission to Europa in the early 2030s would be possible. To make that mission a reality, NASA will need to balance the quantity and quality of the answers it wants with the costs of obtaining them. The intense radiation on the surface of Europa limits the lifespan of any instrument, and mobility increases the cost. The current plan for a Europa lander is a static lander. Because the lander will not be able to move, it will have cricket-like stabilizers rather than firm legs. As such, the lander is affectionately called the Cricket. The Cricket's body is a vault, protecting its sensitive instruments, capable of processing up to 5 samples to answer a series of research questions. Garvin expects that analyzing the first data from the first lander will lead to additional research questions and inspire future missions. Already, there is a discussion of sending a walking rover, a sample return mission, and missions using soft robots. Garvin views the Europa mission as the first of many ocean world explorations. Potential future missions could take us to Saturn's moon Enceladus, or even to Pluto. Garvin concluded by saying that exploring for life in our own solar system will teach us how to look for life in other star systems. NASA is beginning to develop tools for this that can detect spectral signatures suggesting atmospheres capable of supporting life on worlds around other stars. President Milstein then invited questions from the audience. One questioner asked, "Where is the best place to land in Europa?" Garvin responded that a prime target would be around a fresh vent spewing organics. Another questioner asked why the Europa lander was not nuclear-powered, possibly saving money. And Garvin responded that the expected lifetime in that environment is just too short to justify the additional weight for nuclear power. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:47 p.m., President Milstein adjourned the 2,380th meeting of the society to the social hour. Temperature, 25 C. Weather, light rain. Attendance, 106. Respectfully submitted, James Heelan.
Thank you, James. Are there any comments on the minutes or corrections? Seeing that there are none, I will entertain a motion by a member to accept the minutes as read. Jerry, do I have a second? And all those members in favor say aye. Aye. All those members opposed say nay. The minutes are, you want to take your vote back? The minutes are unanimously approved as read and will be posted to the website in due course. We now turn to tonight's lecture. It's my pleasure to introduce tonight's speaker, Antti Pulkkinen. Antti is an astrophysicist and acting deputy director of the Heliophysics Science Division at NASA Goddard Space Flight Center. He is also an adjunct professor at the Catholic University of America, where he served as associate director of the Institute for Astrophysics and Computational Sciences, which he helped found. Antti's research is primarily on empirical studies and first principles modeling of space weather, and on the effects of space weather on man-made systems, not only on the ground, but also in space. He has also been a tireless advocate for education in heliophysics and was instrumental, as I mentioned before, in launching the Space Sciences and Space Weather program at the Catholic University. He is the recipient of a NASA Exceptional Achievement Award and the International Christian Birkeland Medal for his efforts to address space weather effects on power grids. He earned a PhD in theoretical physics at the University of Helsinki, Finland. Please hold questions for the question and answer period at the end of the lecture and join me in welcoming Antti to the podium. on that side.
It's a Mac, it'll work. How many of you has Windows?
You gotta pull something up on your screen.
And we're going to be good to go. All right, looks all right. Well, thanks very much, Larry, and thank you for this invitation. It's really a great honor and pleasure to speak to this audience. I've been working on this specific topic, space weather, for in space physics we talk in solar cycles. So I've been working on these 2 solar cycles. You learn later on exactly how you calibrate that. I've been kind of a strange animal in our field, in a sense that throughout my career I've been playing kind of in the interface between the pure basic scientific research and applied sciences, where we really try to push the scientific research information through what we call research to operations pipeline to the end users, to the industries that are impacted by these things, thereby allowing better hazard assessments and ultimately also tools for mitigation of some of the impacts of space weather that I will be talking about in this presentation. So what I will try to do here today is not only to convince that the space weather is the most important thing in the universe, so that's the primary goal, but the secondary goal is to really kind of give you an idea how what are the key pieces, key science pieces pertaining to the space weather, and also how space weather connects to the impact side, how space weather impacts our infrastructure, both in space and on the ground, and also what we are doing to address these things through this research to operations pipeline. So with that in mind, here's the contents for the lecture today. I always, when I give lectures about space weather, especially for the undergraduate and graduate students, I kind of compare learning space weather as like a peeling of an onion process. You go layer by layer, and through each layer you cry a little bit. So I will use the same method here with you guys, if you don't mind. You don't need to cry, but let's go layer by layer. So we'll start by the very uppermost layer, kind of talking a little bit what is space weather in general, in very kind of general terms, and why we do care. Why a layman should really care at all about the space weather. So let's start that as the first layer, and then we're going to start drilling down a little bit deeper into the details of the science of space weather. So we will be going through some of the space weather fundamentals. No equation side, please. Let's take a show of hands. Who has heard about space weather? Who has heard about solar flares? Almost everybody. Wow, very educated crowd. I'm impressed already. Now I'm nervous. So that's really great. So that allows me to gauge a little bit the content here. But regardless, let's step through some of the basic fundamentals pertaining to the space weather, kind of a conceptual level. Not going too much into an actual theoretical description of any of these things. And what I will try to kind of convey in that portion is that really the space weather is a very large chain of complex interacting domains that we're trying to understand from the first principles based, and ultimately also try to predict how the system of systems, if you will, evolves over time. And then, in the third half, we will talk more about the space weather impact side of things, and then, really drilling down a little bit deeper into the specific types of systems that are impacted by space weather. So that's the overall goal here. Let's start by a definition. How do we define space weather? So here's the kind of a quasi-official version of the definition of space weather, so you can read it from there. It was written down, in the one of the documents from early 90s by the U.S. National Space Weather Program. And really, in general terms, space weather pertains to the evolution of the space environment, the solar conditions, the interplanetary conditions, and planetary magnetospheric conditions, and to the way how those conditions can impact our everyday life, our infrastructure, both in space and on the ground. So really the space weather is kind of a broad umbrella term that pertains to the physical piece, the physics piece of the space physical phenomena, to the engineering piece in terms of how that space environmental and phenomena can impact various systems, and all the way to the operational side of things. How can we take the research information, engineering understanding, and push that through that research to operations pipeline? Am I echoes or something? Okay. And really facilitate the mitigation of these impacts that we experience. And this kind of a nice graphic prepared by our media folks captures really the essence of space weather in a kind of visual terms. So we're dealing with very quite dynamic and in some sense you could say violent sun that has very dynamic features, eruptions taking place that then interacts with the surrounding interplanetary space. It interacts with the planetary magnetospheres like ours here for the Earth. And also interacts and impacts on the systems that we operate not only in space, but also in the atmosphere like the aircraft and also systems on the ground. So all of these pictures here are part of this major space weather umbrella. Then drilling down to that next layer of space weather, let's talk a little bit about broad terms in terms of what are some of the key temporal timescales associated with the space weather phenomena, and let's talk also about some of the key physics types of events that take place in the space environment that we associate with space weather, and then also linked to the actual impacts on various systems. So, broadly speaking, we often talk about 1, 2, 3 punch when we talk about space weather. Those 1, 2, 3 punch pertain to these 3 elements. And the 3 elements are solar flares, in terms which is, and I will talk more about later on, which is really a release of absolute fantastic amount of electromagnetic energy from the solar atmosphere. The time scales of these solar flares are of the order of a few minutes, which is the time it takes for the light to reach from the solar corona to the orbit of the Earth, to maybe a few hours or so. The flares last a few hours or so. Then the second punch pertains to very fast-moving charged particles, what we call energetic charged particles that are also associated with these violent eruptions in the solar atmosphere. The time scales associated with the energetic charged particles are, from about 8 minutes. The very fastest moving charged particles released in these eruptions move almost speed of light. So they reach the Earth in a matter of 10 minutes or so. And some of these, and in the title there's a term ion storm. So these would be your ion storms. They can last for a good several days or so, depending the exact conditions at the time of the eruption in the solar atmosphere. And then the final third punch is what we call the geomagnetic storms, and these are associated with the bulk of material released from the solar atmosphere and interacting with the Earth's magnetosphere, driving very kind of a dynamic changes in the electric current systems in the Earth's magnetosphere. And these things it can last from let's say from few hours to several days or so. Okay, so the time scales associated with these 3 punches are quite different. But there's also wide, broad spectrum of impacts coming from this 1, 2, 3 punch. The flares can impact, so here are the color codes, and here are the associated types of systems in very general, broad terms. The flares can impact global navigational systems, high-frequency signals, energetic, very fast-moving charged particles can impact microelectronics, for example, in an orbiting spacecraft. It can lead to a loss of high-frequency communication signals near the polar regions of the Earth. And then finally, the geomagnetic storm piece has a full spectrum of impacts, ranging from impact on, again, on the high-frequency side communications, to global navigational services, to actual impact on the ground-based infrastructure. This is where we are talking about the impact, for example, on the high voltage power transmission systems. Okay, so that's the kind of the second layer of that space weather onion, if you will. Then I want to spend a couple minutes on talking about the brief history of very high-level attention on this topic, especially here in the U.S. This has been, of course, a topic of scientific research for a very long time, since the dawn of the space age, when we started flying actually the spacecraft, and prior to that. But really the higher level interest on this and higher level actions on this in the US is actually quite a fresh phenomenon. So I'll talk you through some of the key actions, why this is now such a high level thing in the US federal government. Well, the first piece, at least in my opinion, was the National Research Council's workshop that was arranged not long time ago, 2008, here in Washington, D.C. And from that workshop, it resulted in a workshop report, which was Severe Space Weather Events, Understanding Societal and Economic Impacts. And all these documents that I will be showing here are publicly available if you want to Google them and check out the details. This really draw attention to the potential of major impact that we can experience from the extreme space weather events. And in particular, it drew a lot of attention at the highest levels of the US federal government on the potential catastrophic impact on the US high voltage transmission grid. So this really kicked, big wheels to spin in the US federal government, and there was actually a kind of a series of follow-up papers that came from that workshop report. One was published with jointly with North American Electric Reliability Corporation and Department of Energy. Then there was another set of papers or reports that came from the North American Electric Reliability Corporation, and that kind of electric transmission related a series of reports and assessments led ultimately to action by the Federal Energy Regulatory Commission, FERC. And this was a game changer really for space weather in the US. The FERC order, the Federal Energy Regulatory Commission Order 779 that came out 2013, ordered North American Electric Reliability Corporation to develop standards, develop a regulatory framework that will mandate US power transmission industry to be prepared for major or extreme space weather events. Okay, so this means that at this point, the U.S. high voltage power transmission industry, of course, started to pay really close attention to space weather and really trying to understand the space weather. Later on, we got the action from the National Science and Technology Council. This is coming, directly underneath the White House level types of things. And we had a couple reports or documents coming out of it. We had the National Space Weather Strategy, and it had associated document called National Space Weather Action Plan that addressed not only the power grid impact, but impact also on the orbiting spacecraft, impact on the high frequency communications, global navigation systems, and so forth. And this document had actual list of items what the different federal government organizations need to do to address the space weather. Okay. Then the previous administration, the Obama administration, actually had an executive order coming out last year, or 2016 in October. That was a kind of a codification, if you will, of the National Space Weather Action Plan, really saying that, hey, you guys need to follow the action plan. And the final piece to this is that there's actually now a bill on the Hill called Space Weather Research and Forecasting Act. The Space Weather Research and Forecasting Act has now passed the Senate, and it's now going to the House. And hopefully once it passes the House, it will be yet another codification of the National Space Weather Strategy and National Space Weather Action Plan, and mandating U.S. federal government to really take action in addressing the space weather. So in that sense, we're living in one way the golden age of the space weather in terms of the attention that we're getting from the federal government. So it's been really, really kind of an exciting past, let's say 5 years or so in working in this field here in the US. Okay, so with that background, let's go now into a little bit of a more science side of things. So let's talk a little bit about the fundamentals of space weather. What are the key moving physics pieces associated with space weather? From the very fundamental viewpoint, physics viewpoint, the physics of space weather is to a good degree physics of plasmas. Okay, and this is not your typical plasmas in the Star Trek or something like that. The plasma is really, in some sense, the fourth state of matter. Okay, so for those who are not too familiar with this term, if you take a solid block of something, which is a solid state, you heat it up, it will melt, it will become liquid, which is your second state. You add more heat into the system, it will evaporate, it will become in gas, it will be in gas state. And if you add even more heat or energy into your gas, the individual atoms that make up the gas will start losing some of their electrons, okay? And the gas becomes electrically charged. And that electrically charged gas is your plasma, all right? So the plasma is really the fourth state of the matter. And because the electrically charged nature of plasma, the electromagnetic field, electromagnetism plays absolutely fundamental role in dictating how this type of matter actually evolves. So just to get an illustration of that fact, here are a couple images that a lot of people are familiar with. Here on the left-hand side, we have a picture. This is in extreme ultraviolet, which is really a picture of the million degree, about million degree, really hot stuff, plasma. It's hot stuff because it's losing its charges. The matter is losing its charges to become electrically charged. So this is the hot stuff in solar corona. And what you can see here in these loopy structures, and you will see a lot of additional examples of this as we move along here, it's nothing but a reflection of the fact that the matter that is emitting the EUV light in here is organized by the solar magnetic field, okay? So in a way, when you're taking an extreme ultraviolet picture of like this, you're also taking picture of the magnetic field because of the electromagnetic nature of plasmas. Here on the right-hand side, you have another example of similar phenomena. This is a picture of auroras, northern lights or southern lights. How many of you have seen northern lights, by the way? Really many. Great. So I mean that's if you haven't seen it, it should be in your bucket list. The NASA, we had a huge splash about the solar eclipse earlier this year. Obviously everybody paid attention to that. So I know when I gave presentations, I said eclipse it needs to be in your bucket list, but the auroras is the second thing in your bucket list. Okay. And those who have seen it, you know what I mean. But this is kind of a typical shape or form of the auroras. And what is also very typical with the auroras is that you have this ray-like structure associated with it. And that's nothing but the picture of the Earth's magnetic field, okay? So the electrons, the charges that come from the space actually like to follow the Earth's magnetic field, and as they interact with the Earth's upper atmosphere, where they excite the atoms, they also, the emissions will organize per the Earth's magnetic field that organize the precipitation of the electrons that ignite these lights. So again, this is a kind of a picture of the Earth's magnetic field. Another reflection that plasma is really, the evolution of the plasma is dictated by the electromagnetic fields, electric and magnetic fields. Then talking about a little bit about a range of scales here. Especially in terms of the spatial scales and temporal scales. And the point here I'm going to try and make that the range of scales is absolutely vast when you're trying to look at the space weather phenomenon. The relevant time scales pertaining to this plasma phenomena that connect to space weather range from about 10 to the minus 9 seconds. These are like gigahertz fluctuations of the plasma in the solar corona, to 10 to the 8 seconds, which is the length of the entire solar cycle, which is about 11 years or so. In terms of the spatial scales, again, very vast range of scales. The smallest relevant scale, really relevant scales to the space weather phenomena range from about, let's say, 1 meters, which is a typical scale size of ionospheric or plasma structures in the Earth's upper atmosphere, driven by the space weather phenomenon. And again, on the larger side of things, I know we're talking about 10 to the 8 meters or so, which is pretty much the size of the solar system. The largest eruptions that I'll be showing you in some examples can actually fill a good portion of the solar system. Okay, and to complicate things further, there is a strong coupling across the scales. So a lot of these plasmas that are involved with the space weather phenomena are very turbulent. Okay, so there's a very strong coupling between different scales. And for this reason, I think this is one of the more fundamental reasons why understanding and especially forecasting space weather is a really serious challenge. You really need to have to address at the fundamental level all these different range of scales and understand the cross-coupling between these scales to predict space weather. There are a lot of these kind of dynamic processes that we have in the solar system and in the planetary magnetospheres that are associated with space weather. But really fundamentally, the engine, the driver of the space weather is the sun. So let's talk some basics of the sun as they pertain to the space weather. So here's an image I stole from Wikipedia. The first part to this is the core of the sun. Which is where the fusion process operates, turns hydrogen into helium at about 15 million Kelvin. Okay, and this is really the primary engine, but not all of space weather as we know it. This engine generates electromagnetic radiation. After the core comes what we call a radiation zone, which ranges from about a quarter of solar radius to about 70% of the solar radius, which is a region where the transport of the energy takes in the form of electromagnetic radiation. And then comes really important region from the space weather standpoint, which is the solar convection zone, which is about the remaining 30% of the sun or so. And in the convection zone, the most efficient means of transporting energy is not anymore in the form of electromagnetic radiation, but it's the motion of the plasma itself. Okay, so it's really the boiling of the sun, if you will. And I will show examples of how that boiling looks in a couple slides. And this is really important region because that boiling, that motion that takes place in the convection zone, we believe is the source for the solar magnetic field. So the solar dynamo that creates the magnetic field, a very dynamic field, we believe right now is taking place here in the convection zone. So from the space weather standpoint, the physics of the convection zone is really one of the holy grail targets for our research. Then we come, from the convection zone, we come to the if you could call the surface of the sun. This is the place where we have the most of the visible emission of the most of the visible light. The photosphere operates at about 4,000 to 5,000 Kelvin or so, emitting again the light that we actually can see here also on the ground. And then happens the funny thing. So if you look at the kind of the temperature profile here from the core, 15 million degrees radiation zone, 500,000 Kelvin, 6,000, 4,000 Kelvin or so, and you would think that as you go further out, the temperature would keep dropping, but that's not the case in the case of the sun. Once you move further out to the solar atmosphere, something strange happens. Things start to get really, really hot again. So the solar atmosphere, the solar corona here, it actually is at about 1 million degrees again. Okay, so temperature has been rising again. And it kind of gave you an indication of the state of the art in terms of the science of space weather and the space physics. We still do not have good physics-based understanding why the corona is so hot. Okay, so this is the target of state-of-the-art scientific research on this topic. We have a group at Goddard Space Flight Center that is sole focus is to try and understand why corona is so hot. There are multiple theories, of course, for that, from nanoflaring, from wave particle interactions, and all that kind of a good stuff. But we don't have the definitive answer for the reason why the corona is so hot. Sunspots, this is something that is, very significant type of thing from the space weather standpoint, which is really a clumping of the solar magnetic field. And there's this cycle with the sunspots, with this 11-year solar cycle. And these are the regions where we get the very largest eruptions. And then the final piece here is the overall granulation. I will show you actual observational imagery of the granulation, which is nothing but the reflection of this very turbulent motion of the plasma in the solar convection zone as it also generates the Earth's, the sun's magnetic field. So here's a picture, actual observational data of the solar photosphere. So this is ground-based data from a Swedish solar telescope, 1 meter solar telescope. This is at about 430 nanometer wavelength or so. The movie is looping here. The length of the movie is about 30 minutes or so to give you a kind of a sense of scale, how things are evolving in the solar photosphere. And here, if you look at the tick marks, which is the unit of spatial scales, single tick mark is 1,000 kilometers. Okay, so you can easily fit Earth within this dark region here. All right, so we're talking about absolutely massive scales when you talk about solar phenomena. And what you can see here is a kind of a classical signature of what we call sunspot. Okay, so this is a very high resolution photospheric imagery of the sunspot. You will also see these filament structures, which is the penumbra around the sunspot. And these filaments are actually really a reflection, again, nothing but that the magnetic field, the solar magnetic field, organizes the plasma motions. The reason why the sunspots are dark is that because they're a little bit cooler than the surrounding photosphere. They're about 1,000 to 2,000 Kelvin cooler than the surrounding parts of the photosphere. And the reason for that is that the strong magnetic fields that are clumped within the sunspots quench the free flow of the plasmas, and also thereby reduces the heat and energy transport from the solar convection zone to the top of the photosphere. Okay, and that reduced flow of the energy makes the sunspots cooler than the surrounding medium. Another important feature here is the actual granulation. So granulation is really this, kind of a boiling motion. So if you look at this, you really get the sensation of something's boiling, something's really hot. Okay, and that hot stuff that is boiling there is the solar plasma that transports the energy, heat from the bottom of the convection zone to the top of the convection zone, and ultimately through the photosphere of the sun. The sunspots have a certain cycle. The number of the sunspots, if you take a picture of the sun and calculate the sunspots, that total number of the sunspots will evolve over time scale of 11 years. Okay, so we've been doing sunspot observations really from the 1600s. This is when folks like Galilei first time turned their telescopes and started to look at the sun and counting these very strange spots there. Of course, they had absolutely no idea at that time what those were, but we have records of these things from the 1600s. All the way up to now. And one of the more predictable behaviors of the sun is that the number of sunspots evolves over time, and there's a strong modulation of that sunspot number at about 11-year length. Okay, so when I say that I've been in the field for 2 solar cycles, now you have the actual calibration to real years. Why the cycle is important is that when you have large number of sunspots, okay, clumped in the solar disk, it also signifies that there's additional complexity to the solar magnetic field. You have these additional concentrations all over in the solar atmosphere. Okay, and that additional complexity in the solar magnetic field translates to a larger chance for having eruptions from the solar atmosphere. So, when you're at the top of the solar cycle, when you have a lot of sunspots, there is an increased likelihood for having major eruptions. When you're at the bottom of the solar cycle, when you observe few, if any, sunspots, then there is a significantly reduced likelihood for having any kinds of major eruptions. And actually right now, as we speak, we're about maybe 2 years or so from the next solar minimum. Okay, so we're kind of approaching that in some sense boring part of the solar cycle when there is a significantly reduced chance for having some of these major eruptions. Well, how do the major eruptions look like? One of the basic, the key fundamental processes in terms of the eruptions are the solar flares that I mentioned already earlier on. Solar flares, which are a release of massive amounts of energy from the solar atmosphere, are kind of eruptions that take in the time scales of the order of 60 minutes. And in a single eruption, you can release energies of the order of 10 to the 25 joules. Okay? To give you a point of reference, the approximate annual world energy consumption is about of the order of 10 to the 20 joules. Okay, so if you could capture and bottle single flare eruption, you could power Earth for a few thousand years. Okay, or all our energy problems would have been solved. Bing. Unfortunately, we cannot do that, at least not yet. So let's look how the flares look like. So this is now data from Solar Dynamics Observatory, which is one of our NASA flagship heliophysics missions, still orbiting in space, taking real-time, non-stop imagery of the solar atmosphere. This is data from, I believe this is 193 angstrom imagery, which is again imaging the few million degree plasma in the solar atmosphere. And what you see here are kind of a classical signatures of the solar eruption. So if you look at here the southwestern portion, you see this eruption, and then you have the zoomed level of it. You will see very complex magnetic field structures, and then, boom, you have a massive release of electromagnetic radiation, which we can image in the extreme ultraviolet using missions like Solar Dynamics Observatory. And that single boom releases that 10 to the 25 joules of energy. Okay. The second core phenomena pertaining to space weather is called coronal mass ejections. Okay. Or CMEs. The CME is probably the most famous acronym or jargon that we use in the space weather. These things are a little bit different from the flares. So in the flares, the most of the energy release takes place in the form of electromagnetic radiation. In the case of coronal mass ejections, or CMEs, the major release of that solar energy takes place in the form of bulk motion of the plasma. So you have billions of tons of solar atmospheric material that is thrown out to the surrounding heliosphere at 1,000,000 miles per hour or so. And in SI units in terms of several hundred kilometers per second to even several thousand kilometers per second. Just imaginable kinds of speeds for such a large masses. And to show you an example how these things actually look, I will show you an imagery from another flagship heliophysics mission called STEREO. So in the center we have STEREO extreme ultraviolet imagery. And then we have also another kind of instrument taking pictures, which is called coronagraph. Coronagraph creates an artificial eclipse by blocking the bright solar disk so that it can image the dimmer structures in the atmosphere. And by kind of stitching together the extreme ultraviolet imagery and the coronagraph imagery, you will get the kind of a full story how these eruptions now CMEs, evolve in the solar atmosphere. So here's a classical CME. Again, to give you some of the time scale here. Let's see. It's not this guy. This guy. Well, the time scale runs here, but the whole sequence it's going in the loop is about 5 hours or so. Okay, so you have these structures moving from the solar atmosphere out to to 5 to 10 solar radii in a matter of few hours. Okay, very fast moving stuff. So you will see in the extreme ultraviolet you have a lifting of this material, and then it turns in this huge blob which is the billions of tons of the solar material, that then starts to really kind of plow through the entire solar system. And these guys, they evolve into these solar system size types of things. Okay, and the interesting thing here is that the physics that actually triggers these things takes place in the microscales. Okay, so it's like you bend the rubber band, and then you have a small perturbation there, and bang, it goes off. Okay, the similar kind of thing here. You pump all this energy in the solar atmosphere up to the critical threshold, and then minor instability, microscale instability, launches the whole gigantic thing. Okay, so that's a very good illustration of that cross-scale coupling. Okay, so to understand, for example, the initiation and buildup of the coronal mass ejections, you need to understand the physics from that microscale all the way to the scales of the entire solar system, which obviously is a pretty interesting challenge. So let's then start to move closer to the locations where we Earthlings live. Here's another animation which shows really the interaction between this plasma coming from the sun and the Earth's magnetic field. You will see that a lot of this plasma that flows from the sun is actually kind of diverted around the Earth. And that diversion is caused by the Earth's own magnetic field. Okay, so our Earth's own magnetic field shields us from a lot of the violence that we're getting from the sun. Okay, but there are regions where the mass, energy, and momentum can actually enter the Earth's magnetic field, through processes like we call the magnetic reconnection, which changes the topology of the magnetic fields and kind of opens up the Earth's magnetosphere, thereby allowing this transfer of mass, energy, and momentum into the system. This is actually one of the reasons why we think that Mars started to lose its atmosphere. When Mars lost its magnetic shield, this solar wind and all these blasts coming from the sun could interact directly with the Martian atmosphere and leading to a Martian atmospheric escape. So in a way, our own magnetic field is really shielding us from the sun. So when you have the entrance of the mass, energy, and momentum into the system through, for example, the magnetic reconnection process that opens up parts of the magnetosphere, so not all energy is diverted around the Earth. There's also entry of a small fraction of the energy. That small fraction of the energy creates a lot of different kinds of dynamical phenomena within the Earth's magnetic itself. And one of the dynamic phenomena that has been observed since the early 1800s is related to the electric current systems. So all this interaction between the solar wind and the coronal mass ejections and the Earth's magnetic field creates massive million ampere electric currents that flow in different parts of the Earth's what we call magnetosphere. And the variations in these electric current systems can be observed on the ground in terms of the magnetic field fluctuations. And those magnetic field fluctuations we call geomagnetic storms. Okay? And the geomagnetic storms were really the first observed direct space weather phenomena in the kind of, you could say, more modern-ish type of age. Here's an example what the magnetic storm looks like. So you have a coronal mass ejection interacting with the Earth's magnetic field, driving all these electric current systems, and then creating the fluctuations in the magnetic field at the surface of the Earth. And this is how it looks like. So here I have data from a ground-based geophysical observatory in Abisko. This is in Northern Europe, one of the geophysical observatories over there. And it measures the magnetic field at that location. So I have here actually the X, Y, and Z component, which is the three Cartesian components of the magnetic field fluctuations at that location. And I have 24 hours worth of data here with a 1 minute temporal resolution. So you can see here at the beginning of the day of the October 29, 2003, which is the famous Halloween storm period, which actually caused a lot of space weather impact on our ground-based and space-based infrastructure. I'll be talking in a couple minutes. Before the storm period, the measurements in terms of the magnetic field were quite flat, nothing too interesting happening. And bam, then the action starts. You will have thousands of nanotesla fluctuations in the magnetic field observed in Abisko. And this is the classical signature of the geomagnetic storm. the magnetic field fluctuations associated with interaction between the coronal mass ejections and the Earth's magnetic field. And then the final piece really to this fundamental physics portion is the interaction between coronal mass ejections, flares, and the Earth's upper atmosphere. Okay, I usually show this slide to my grad students just to scare the hell out of them, and hopefully you guys are not too scared. But the key point here is that it's really complex. Okay. The idea here is that you will have all this energy being pumped from the solar phenomena in the form of electromagnetic radiation that gets absorbed in the upper atmosphere. You have charged particle penetration, precipitation into the Earth's upper atmosphere. You have electromagnetic interaction between plasma within the Earth's magnetosphere and the upper atmosphere. And all that drives this very complex reaction of the Earth's upper atmosphere motion, not only plasma, but also coupling with the neutrals of the upper atmosphere, causing different kinds of interesting phenomena there as well. Example of which is ion and neutral escape. Okay, so we have stuff flying out of our atmosphere. So this is yet another form how the atmospheric loss can take place. Okay, so through the interaction between the Earth's magnetic field and the coronal mass ejections, there are some processes that pump energy into the Earth's upper atmosphere and can push the neutrals out. Okay, and that of course relates to let's say to exoplanetary research and to understanding loss of the atmosphere like that of a Martian environment. So that's kind of a quick run through of some of the basic physical pieces pertaining to the space weather. Hopefully you got a little bit of an idea about what are some of the key physical pieces pertaining to that. But the fundamental idea here is that it's a vast and complex chain of interacting domains, operating at vastly different types of spatial scales and temporal scales. And we need to understand all that in order to predict space weather starting from the first principles. Let's then start to look at more on the impact side of things now that we have the fundamentals in our belt. And let's start, let's say, you could say, kind of like a more entertaining aspect of space weather. So not all space weather is scary and dangerous. Okay, so there's also the fun part to it. And the fun part really is the aurora borealis and aurora australis, the northern lights and the southern lights. This is maybe the first space weather phenomena that humans ever observed. So when we lived still in the caves, and we didn't have cell phones, or we didn't have a plug where we put our toaster, this was our space weather impact. Okay, so we were owing the auroral displays. And these things are caused, again, through the interaction between the solar eruptions and the Earth's magnetic field. And you have a precipitation of, in this case, electrons coming, following the Earth's magnetic field into the Earth's upper atmosphere, interacting with the material in the upper atmosphere and igniting the northern lights and southern lights. But in addition to this, you could say the entertaining aspect, there are also the hazardous aspects of space weather. And this is kind of a classical illustration of some of the key concerns that we have pertaining to the space weather. And we'll talk a little bit more in detail a few of these. The major ion storms or energetically charged particle events can be a hazard for spacecraft. They can also be a hazard for humans in space. The changes in the upper atmosphere because of this energy pumping into the Earth's upper atmosphere can create trouble in terms of communicating, pushing the electromagnetic signals through this medium. The airline operations can be impacted because of the impact on the high-frequency communications and charged particle radiation. And ultimately also systems like power grid can be impacted by space weather. So there is a whole host of things, whole spectrum of kinds of things that are actually impacted space weather, one way or the other. And it is actually fairly common tendency that every time we come up with a new fancy technology, let's say power transmission grid, global positioning systems, cell communications, we find out later on that they are exposed to the fury of the sun in terms of the space weather impact on those kinds of modern systems. From the NASA standpoint, one of the key concerns, of course, is the impact on the spacecraft. The spacecraft it's really mostly related to the charged particle radiation, to the ion storms. The charged particles can create charging of the spacecraft, and if you have discharge of that charging, that is a bad thing for the electronics of the spacecraft. You can have a single very fast-moving protons or heavier ions going through the spacecraft and causing single event upsets, which is not a good thing. The pumping of this energy to the upper atmosphere can actually heat the upper atmosphere, and that heating of the upper atmosphere can make the atmosphere expand. Okay, so your low Earth orbiting spacecraft can actually be exposed to increased atmospheric drag because of this heating. And this is a major and growing issue for the conjunction assessments. I'm sure maybe you even had a talk about the space debris. And the space debris is an increasing concern. And when you have major geomagnetic storms, major space weather storms, because of the atmospheric drag effects, we lose track of some of those objects. Okay? And that can be a really hazard if you're trying to avoid and maneuver your way around the debris in the path of your spacecraft. Total dose in terms of the total impact of the radiation to systems like the solar panels is a concern. And then also in some cases the geomagnetic storms and the impact of the charged particles, for example, on the star trackers can lead to effects on the attitude control systems of individual spacecraft. And then of course from the human space exploration standpoint, we are worried about the radiation concern. So the same energetic charged particles that can create single event upsets for robotic systems can be a hazard for biological systems in the form of ionizing radiation. Okay? So the folks in space are exposed to this elevated radiation. Now, since we are operating right now only at the low Earth orbit with the International Space Station, and International Space Station is well within the Earth's protective magnetic shield. So it's very well shielded, actually, from a lot of that radiation coming from space, coming from the sun. But once we go, hopefully soon, go beyond the LEO again to lunar missions, maybe asteroid capture missions, and ultimately, hopefully, also to Mars, we will be operating in the deep space conditions. We don't have the Earth's magnetic field shielding us anymore. And at that point, the radiation hazard and space weather is one of the key concerns that we need to address to make those kinds of missions possible in first place. The same charged particle radiation can also be hazard for airline operations. So here's actual data from a radiation or the solar event that took place during a flight from Frankfurt to Dallas. And here's the data. The green or the blue line shows the data of the radiation levels that we observed with the neutron monitors here on the ground. The red line shows the recordings of the radiation levels on board that flight from Frankfurt to Dallas. And then the green line then shows us the altitude of the aircraft. And you see that, when the aircraft got to its cruising altitude about maybe 35,000 feet or so, you could see that the baseline radiation increased in terms of the observations. And this is the galactic cosmic ray background that is always there. Okay, as you go higher in the atmosphere, you will always experience higher levels of radiation. But then at about 2 p.m. UTC or so, the actual energetic charged particle event because of the solar eruption kicked in, and you could see that the radiation levels observed both on the ground in terms of the neutron monitors and also in terms of the radiation monitoring on board the aircraft increased. In terms of the aircraft increased about a factor of 2 or so. Okay, so we actually observe these radiation events on commercial aircraft. So this is obviously a concern, and we still are in the process of trying to understand how significant this risk is, especially for the crew that flies a lot, and also through the polar regions. Well, that's just the example of the deep space conditions. So we are actually already making plans how do we mitigate the radiation hazard in the deep space conditions. And right now, one of the plans is that when we go to the deep space conditions, we will have storm shelter. Okay, and this is one of the concept of a storm shelter developed by our NASA Langley Research Center colleagues, where when the crew gets information that there's a major solar eruption, they will enter this, you could say, little box to shield from the radiation, to cut the dose levels to the minimum possible level on board that spacecraft. And once they get all clear message from that the event is over, then they can actually exit the storm shelter. So the shelter is already being seriously considered for deep space missions. I mentioned the GPS and the changes in the upper atmospheric conditions because of the space weather, and that leads to a whole host of kinds of systems that can be impacted. The changes in the upper atmosphere, especially in the ionospheric conditions. Ionosphere is about this electrically conducting part of the atmosphere at about 100 miles above the surface of the Earth. Changes in the ionosphere during the space weather storms changes the way how electromagnetic signals bounce off of the ionosphere and how they pass through the ionosphere. And that change can lead to problems to systems like global navigation satellites. You can get ranging errors, or in worst cases, you may lose lock altogether because of the disturbances in the ionosphere driven by the space weather. High-frequency radio communications can be interfered because of the changes in the ionospheric communications. And this is actually the concern number one from the space weather standpoint for the U.S. airline operators. A lot of the operators that fly through from North America to Asia these days cross the poles. Okay, and energetic charged particles during these space weather storms can actually create high-frequency radio blackouts in the polar regions. Okay, and if you have a high-frequency radio blackout right at the polar region where you cannot see the geostationary communication satellites anymore, you don't have any communications. No communications whatsoever, you cannot fly through. So when you have major space weather events, a lot of the airlines actually have to divert around the polar routes, and of course, that's an increased use of fuel and so forth. There's a lot of cost from that kind of diversion to the airline operators. And also other kinds of communication systems, even the cell phone communications can be impacted by space weather. And the final piece here, in terms of the systems that can be impacted, are the power grids. The power grids are getting a lot of press these days. So let's talk about how these kinds of systems can be impacted. So here's a graphical illustration of the mechanism how space weather can impact the power grids. So I mentioned that when you have these massive coronal mass ejections interacting with the Earth's magnetic field, they create changes in the electric current systems in the Earth's near-space environment. So in this graphical illustration, those electric current systems are indicated by this loopy current here. Okay, so here's the ionospheric upper atmospheric portion. Then you have what we call field-aligned currents that bring the charge from the outer parts of the magnetosphere into the upper atmosphere. When you have large geomagnetic storms, there are large variations in the electric current systems like this. The amplitudes of these currents can be of the order of millions of amps, and they vary at the time scales of seconds. Okay, so those kinds of violent changes induce an electric field on the surface of the Earth, and that electric field we call the geoelectric field. And now if you have a conductor system on the ground that is grounded at 2 points, this electric field will create a voltage drop across the terminal. And that voltage drop will drive an electric current in your conductor. Okay? And that conductor could be buried gas and oil pipeline, it could be a railway system, but it could also be high voltage power transmission system. Okay? So it's really the electric field driven by the variation of the electric currents in the near space that then drives the current in the conductor, and those currents in the conductor we call geomagnetically induced currents, or GICs, that again can flow in buried gas and oil pipelines, in railway systems, and also in high voltage power transmission systems. And in worst cases, the high voltage power transmission systems can really be exposed to this problem. Okay, The power system, electric power systems that operate at AC, 50 or 60 hertz, living, depending where you live, don't like extra currents flowing through them. It's really bad for them, okay? And the extra current that flows through the high voltage power transformer causes so-called half-cycle saturation. And that half-cycle saturation can lead to a heating of the transformer. In worst cases, that excessive heating can lead to a permanent damage of the transformer. So here's actually an example of a transformer from South Africa that got damaged because of the GICs during this Halloween storm of October 2003. And also these extra currents can create voltage fluctuations and in some cases even voltage collapse of the system. By far the most famous example of the space weather impacts is the collapse or the blackout in Quebec area in Canada during the storm of March 1989. And that electric blackout was caused by the voltage collapse, the half-cycle saturation of the transformers in the Canadian region, driven by the GICs, which in turn were driven by the geoelectric field in that geographical area. And this is really the major focus right now in terms of trying to understand the hazard that the space weather poses on our infrastructure. Obviously, virtually every aspect of our lives is dependent on the reliable transmission of electricity. If we don't have electricity, in a few days there will be chaos, okay? And that is one of the big concerns, and the driving engine behind the higher level federal government action that I mentioned in the beginning portions of my lecture. So, we see that the space weather is really trying to understand how the solar activity influences the conditions in the interplanetary space, the plasma evolution of the interplanetary space, how the solar activity couples with the evolution of the planetary magnetospheres, the evolution of the electric currents in the planetary magnetospheres, and some of which will actually couple all the way to the surface level, couple with the Earth's magnetic field and create magnetic field fluctuations, induce geoelectric fields and geomagnetically induced currents all the way on the surface of the Earth. So we talk about sun to mud kind of physics. So really it is sun to mud. We need to understand everything between sun and the Earth. And then also how the space weather is how this space physical phenomena couples or interacts or impacts our infrastructure and in space and on the ground. And really the fundamental driving engine for a lot of the heliophysics research and space weather research is to understand how exposed are we to the fury of the sun and how we can mitigate these impacts on various systems. And for those reasons, we fly all these birds, providing the observational information. We build all these models to understand the fundamental physics of space weather, to provide, enable the more advanced mitigation tools for us to mitigate the impacts of the space weather. So with that, I thank you for your attention, and I guess we'll have some Q&A.
So I'm sure we have time for a few questions. But before we take questions, I want to tell you about our procedure, so that those who are listening in will be able to hear the questions, and those in the audience will be able to hear the questions. There are people with microphones around the room. And if you have a question, if you please raise your hand long enough for somebody with a microphone to bring it to you, and then I will call on you, and then you can ask a question. A question, no speeches. Questions. All right, we got a question there.
Yes.
Oh, please tell us if your name and if you're a member or not.
I'm Joseph Powers, and I'm not a member. I wondered if there was a possibility for, say, a sample return mission from the moon or Mercury or someplace to acquire a longer historical record of this by like taking core samples from rocks at different ages to see the time evolution of these cycles beyond the 400 years that you had there. So is there any possibility of that, and what would that be like?
Yeah, there is possibility of that, and maybe in that context, even more interesting is to do the similar thing here on the Earth. And that's exactly what we have done. So we have, for example, ice core samples. We have tree rings telling the story of the space weather conditions, going hundreds of years back in time. So we actually have sampled the Earth, and the ice core samples can give us information about the millennium of the evolution of the electric charged particle conditions in the space. So the idea is absolutely correct, and that can be implemented also in the context of other planetary environments like lunar conditions, Martian asteroids, and so forth. But one of the more interesting data points, at least in my mind, come from here, our own planet, where we are doing exactly those kinds of assessments.
Good question up here. Wait for the microphone. Stand up.
Hello, David. I'm David Rosen, a lifetime member of PSW. First of all, in the 19th century, were there any times that the telegraph or something was messed up because of the solar flares, and did they know what was messing it up? And second of all, could the 22-year cycle, it's really a 22-year cycle, be driven somehow by the orbit of Jupiter, which is about 12 and a half years? I mean, what causes this 11-year cycle?
Sure. So in terms of the impacts on the 1800s, indeed the telegraph system was impacted by space weather. Probably the strongest geomagnetic storm that we have on record is from 1859. And during the 1859 storm, there are documentations of telegraph operators seeing that there's absolutely crazy noise in the system, and they in some instances they actually disconnected the batteries, and the telegraph system still kept operating. Of course, they have absolutely no idea what was going on. In the 1800s, there were some ideas that all this is somehow related, at least to auroras, because in some instances, especially at the higher latitude locations, there was a kind of a good temporal coincidence between what they're experiencing in the telegraphs and in terms of the aurora borealis. But the more detailed understanding that it actually is driven by the solar phenomenon was not really there. There were some correlation assessments that people were analyzing the impact on the telegraph system and the sunspot numbers, kind of speculating that could this be the cause, but there was no detailed physical understanding of this. But definitely the impacts were observed already back then. Now, in terms of the 11-year solar cycle, we think that we have some fundamentals of understanding that the generation of that cycle, and it's really the interplay between the differential rotation of the solar plasma in the convection zone and the turbulent convection in the convection zone that gives the rise to this kind of interplay between different effects, which we call is alpha omega dynamo. And the solar dynamo models that have physics of that alpha omega are actually capable of reproducing this oscillating behavior of the solar magnetism. So we have some fundamental idea that what is the root cause of it, but there's a lot of still details to be figured out, especially in terms of trying to predict the magnitude of the next solar cycle. We don't really understand what are the key physics we need to capture to be able to predict the amplitude of it. But we have some fundamental understanding what is the cause of the oscillation.
So we have Carl. Then we have a man in a
Carl
blue
Merrill.
t-shirt.
I'm a member of the society. I'm impressed by the number of conferences they've had and all the reports. But the real problem, as I understand it, is that our electrical system is privately utilities. And I've heard that they've really not taken the steps necessary to harden the system. And in addition, not only is the problem due to problems from the sun and electromagnetic storms, but from a hostile other group that would set off a nuclear device high in the atmosphere. Yeah. So could you comment, have we taken any steps to harden this? Sure.
And I actually really appreciate this question, because there's a lot of misunderstanding, I think, on that exact point. For full disclosure, for all these 2 solar cycles that I've been working on this topic, I've worked in very close collaboration with the utilities, in Europe, in Japan, in other continents, and also in North America. And I can say that I'm very proud especially about the U.S. utilities, because of the FERC actions right now. utilities are really paying attention and they're taking action to understand this. A lot of the US utilities have already operational mitigation procedures in place to minimize the impact. Many utilities are getting information from NOAA, Space Weather Prediction Center, which is our nation's official source for space weather prediction information. And based on their assessments and their own observations of these induced currents that they measure, more and more of them measure these induced currents flowing through their transformers, they will actually trigger actions. Okay, so they are reacting to this. Okay, and also in the framework of the regulatory action in this, all U.S. utilities operating above 220 kV systems are required to do hazard assessment. So all U.S. utilities are required to take action on this. Actually the first part of that regulatory framework pertaining to the hazard assessments passed earlier this year. And over the next 5-year period, all U.S. utilities operating above 220 kV have to do a detailed assessment and have to have operational mitigation plan to mitigate the impact if it's deemed significant enough. So I think this idea that the U.S. utilities are not doing anything is not accurate. So I think the U.S. utilities are doing a lot to address this issue, and then they have very advanced understanding. Of course, there are still utilities out there that are like, what the heck is this? But more and more U.S. utilities are quite familiar with this phenomena. I spent countless hours going to the North American Electric Reliability Corporation meetings with the Electric Power Research Institute, and those kinds of things to try to educate that audience about this physical phenomena. So I think the U.S. utilities are already very well educated, and they're becoming more and more educated over the next 5 years. Oh, and you had the EMP thing. So yeah, it's really interesting. So for those who are not familiar with this idea, the nuclear detonations high in the atmosphere, which has really kind of 3 components to the electromagnetic signal associated with it, E1, E2, and E3. The E3 portion of it is actually looks very much like a geomagnetic storm. Okay, so the amplitude of the magnetic field fluctuations and the temporal evolution of the electromagnetic signal from that E3 component looks very much like a geomagnetic storm. So that's why, for example, also in some of the actions on the Hill, the space weather and the EMP have been clumped together, and the idea is that if you do something for one, you will at the same time address the other. So there is that physical connection, but on our side, I've been focusing strictly on the natural hazard, the natural phenomenon, but there is that kind of from the signal processing standpoint, the similarity to the EMP phenomenon. You're absolutely right about that.
So we have one of the blue T-shirt there.
Bob Hershey, I remember.
Okay.
What would a worst-case 100-year event look like from the statistics you got?
Well, once in a 100-year, the rule of thumb, if you go back here, oh yeah, you switched the screen already.
I can bring it back.
Pardon me?
You want me to bring it
No,
back?
it's okay, Larry. So I have a rule of thumb in terms of this. So the geoelectric field was the primary quantity that drives the induced currents that impacts the transmission systems, right? So the rule of thumb that I have for the geoelectric field magnitudes is that 0.1 volts per kilometer, nobody cares. 1 volts per kilometer, people start paying attention. 10 volts per kilometer, lights out. Okay, and it turns out when you do the statistical assessment of these geoelectric field amplitudes that you're actually pushing closer to that 10 volts per kilometer kinds of scenarios. So in a once in a 100-year type of a situations, there is a very good chance that we will experience some blackouts. So it's getting quite close to that lights out kind of a threshold idea.
So I have a question up here.
Hi, I'm Cynthia Angel. I'm not a member. Thank you very much for this interesting lecture. I had a question. We know that the solar cycle is 11 years and we can anticipate that, but is there any way to try to anticipate geomagnetic storms? Is there any predictive studies done?
Yeah, so right now the state of the art in terms of forecasting space weather is that we're in one way we're in a reactionary mode. Okay, so we cannot predict the actual eruptions in the solar atmosphere before they take place. There are some statistical models that say there's an increased likelihood of having eruption, but we really honestly we don't have capability to predict the eruption itself. Okay, once we see the eruption taking place with the kind of imagery that I showed in my lecture, then we can go into into a forecasting mode. So it takes about, depending on the violence of the eruption, it takes, from 20 hours to maybe 40 hours, these coronal mass ejections to reach from the solar atmosphere the orbit of the Earth. Okay, so that's our forecasting. So now we have tools. We have the observational tools to observe these eruptions taking place, and we have modern models that we can use to propagate what I call sometimes the space hurricane models, because there are a lot of analogies there. We have space hurricane models that allows us to take that observational information and project time to the future. What are the locations in the solar system we're expecting to be impacted by the corresponding coronal mass ejection? What is the time of the arrival? What is the time of the impact of the coronal mass ejection at these different targets? And then also we have some initial ideas how to predict the magnitude of that impact. So in the context of the geomagnetic storms and the impact on the transmission grid, for example, we have now tools to give you some heads up, of the order of 20 hours in advance or so. But in terms of the flares, the electromagnetic radiation itself, we would have to predict the eruptions themselves, and we quite can't do that yet. We're not there yet.
A question over here on the right, yeah.
Hi, my name is Tej. I'm a guest. So why is there a lot of delay in the magnetic currents reaching Earth compared to the light? Because it's traveling to the same medium, right?
I talked about this, 1, 2, 3 punch. So the first punch was the electromagnetic radiation, which propagates at the speed of light. Okay. The second the part was the charged particles, the energetic charged particles, and the most energetic charged particles all travel also almost speed of light. Okay. But the clouds, the coronal mass ejections, these are motions of the bulk plasma, the motion of the material. It's not just the electromagnetic field. It's a motion of the bulk material, and that is significantly slower motion than the speed of light. So the speeds of these bulk motions are of the order of some hundreds of kilometers per second. In some extreme cases, maybe 2,000-3,000 kilometers per second, which is of course it's just fantastic speed for large amounts of material, but it's significantly slower than the speed of light.
James?
Hi, I have a question from someone on the internet on the West Coast. I'm James Heelan, by the way, member. The question is, the current quiet period of the sun seems to coincide with a real explosion of satellite and commercial space activity. Mm-hmm. Are we headed for trouble as these efforts come to fruition right as conditions begin to deteriorate?
That is interesting and very complex question. Honestly, I don't know.
Wait. Who was it? You're supposed to say their
West
name
Coast?
and whether they're not.
Which president?
It was Preston in disguise.
Okay, so that's that's a very complex question, and the honest answer is that I don't know. Our shop, NASA, we have certain specifications for the radiation tolerance. So when we design spacecraft to fly in different environmental conditions, we have fairly strict the specs and design criteria, for example, for them to withstand energetic charged particle radiation. Okay, so on our side of things, we're going to be okay because we understand we've been seeing this going on, and we have spec limits for it. But for the commercial operators, that can be a different story. Okay, a lot of the commercial operators might not be aware of this hazard. Indeed, and indeed, once you go through the solar minimum, when there's a lot of loss of attention on this issue, you may have new operators coming as late that are not necessarily designing their systems to the same specifications, and that would then spell trouble later on as we again start climbing towards the next solar maximum. So I think that's a very good question. I think it's an open question. I can say from mostly from the federal government side of things, definitely from the NASA side of things, we're going to be okay because we have certain specifications where we design our systems. But for the new operators that are not necessarily as well educated on these things, that's a question mark.
Last question, I think, would be William.
William Worley,
Stand
member.
up, can you?
What's the relationship between space weather and climate change? Isn't the sun more powerful than CO2?
That's another good question. There's been a lot of research on that specific topic. We know that major space weather storms can change the atmospheric conditions. Okay, I mentioned that. One of the changes is that there can be a depletion of ozone in the stratosphere. Okay, so we've observed energetic charged particle events leading to a temporary loss of ozone in the stratosphere, which of course then influences the atmospheric dynamics themselves. We've also had researchers indicating that strong energetic charged particle events and the galactic cosmic rays can actually provide seeds for the cloud formation. Okay, and that would of course then also couple to the climate types of questions. So there are ideas how the space weather might be able to couple to the overall terrestrial weather and the climate system, but I think that the jury is still out there for this. We really don't know. The current thinking right now in terms of the overall climate change is that the space weather modulation of that is probably very small compared to some of the other sources. But this is very state of the art kind of a question and state of the art research topic that we're trying to kind of investigate right now.
So I think that'll be our last question. But before you go, I have a present.
Okay.
So we have a framed copy of the announcement of your lecture signed by all of the members of the General Committee as a kind of thank you for coming here and giving us this lecture.
Thank you very much. Appreciate it. Thank you. All right, thanks very much.
So there are a few closing announcements before we go. First, I want to thank all our members, sponsors, and supporters for keeping PSW going and growing. PSW depends on enthusiastic, active, and capable members and supporters, and on our sponsors. Without you, PSW would not be able to continue and would not provide these free lectures. So please join if you're not a member. And if you are a member, please donate. If you want to become a member, it's easy. You just go to our homepage, which is only going to look like this a little while longer. So if you really like this page, then you should go there now. Okay, and you'll notice it's current lectures, archive lectures, Henry lectures about PSW, presidents, officers, membership. And you hit on the membership button, believe it or not, and pulls up, guess what? The membership application. So if you will fill out the application, give us just a little information about you. There's no IQ test, and there are no high barriers to membership. Membership is open to anybody with an interest in science. And when you get down to the bottom of your membership form and you've filled out all the required fields, you'll get to the Submit button, which will take you to a payment page. You can pay with any credit card. You do not have to pay with PayPal. You do not have to use PayPal. And you do not have to like PayPal. So this is a standard payment page. Just read what it says and follow the directions, and your application for membership will be submitted, and you will be notified in due course that you have been accepted as a member. Just keep in mind that PSW is not really aimed at philosophy. They're interested in science and technology. Okay, so, and PSW is a nonprofit educational organization, tax exempt under Section 501c3 of the Internal Revenue Code. Next lecture, coming up on November 3rd, will be the 2,382nd meeting. It'll be right here in the Powell Auditorium. The speaker will be Byron Cook. He is a senior principal at Amazon Web Services. I'm not exactly sure what senior principal means, but I'm told it means he's pretty high up in the hierarchy. And he is a professor of computer science at the University College London. His talk will be on automatically proving that computer programs do what they're supposed to do. Now, there was another title previously, but it referred to a product of another company. And so I was admonished that I should change the title. But part of what these predictive programs do is they prevent crashes, which means that you don't see a certain beach ball and you don't see a certain colored screen as much anymore as you used to. And part of what makes it interesting is that people had previously said that it was impossible to design a program that would predict these unpredictable events and prevent those bad outcomes of the programs that would freeze up your computer. So Brian's talk should be pretty interesting, and I hope you'll all come and hear what he has to say. The rest of the fall schedule has been posted to the website, for the most part with the abstracts and bios, although I'm having a little trouble extracting those from some of our speakers. So the next speaker after Byron will be Jerry Joyce, who is at Salk and head of the Novartis Genomics Institute. And his talk will be on Life 2.0. He is one of a variety of people who are trying to recreate many of the aspects of life in the test tube in a completely artificial system. After that, on December 1st, we have Nima Arkani Hamed of Princeton at the Institute for Advanced Studies. And his talk is going to be on physics beyond the Higgs. Although he sent me a title recently, and it was The Death of Space-Time, which I thought, well, that would be unfortunate. And then we have Douglas Smith of Duke, who is going to be speaking on metamaterials, cloaking and perfect lenses. And finally, we have the President's Lecture on 5 January of next year. And I'm hoping the speaker will be a professor named Aviv Regev, who works on genomics of single cells and is rewriting the book on cell diversity. And with that, I believe I will, yes, one more announcement. Social hour. Social hour, to which we're going to adjourn, ends at 10:30, after which PSW members and their guests meet at the Fairfax Hotel Lounge across the street. If you want to join us, please speak with Corresponding Secretary Robin Taylor, back of the room, Vice President Lloyd Mitchell, or myself, and they will tell you how to get there. Please use the side entrances to exit the building, and I will now accept a motion to adjourn the 2381st meeting of the Society to the social hour. Do I have a motion, or do you all want to stay here and listen to me? Jerry, okay, a second? All in favor? All opposed? Meeting is adjourned.